Hi everyone, I'm Junhao Jiang. I'm a junior student in computer engineering department. Today I'm going to present my summer research experience running software on broken hardware. I've been working with Andrea Pellegrini, who is a second-year PhD student, and Professor Valerio Botago. First, problems in computer hardwares. The picture here is the physical layout of an Intel Pentium 4 microprocessor, which has a single core in it. And then Intel developed Core Duo, which we can find in most of the laptops today. And then quad-core. As we can see here, the complexity of those microprocessors keeps growing, and the number of logic components in it is becoming larger and larger. So here comes the problem. Those microprocessors are more likely to be designed and manufactured with bugs in it. Those bugs could have appeared in the design processes or in the manufacturing process, or even after we have used them for a while. Normally, people at Intel, AMD, and etc. would use verification to verify the circuits. However, as the complexity grows, formal verification, which is a complete test of the circuit, would take months or even years to finish, so people won't do that. Thus, microprocessors with bugs might go into the market. And that could result in software errors. And if the software don't detect them, they just give you wrong results. So here's our solution. Use software test. We are working with a group of people in University of Illinois. And basically, our project has two parts. One is software detection mechanism, which is under development by people in University of Illinois. And the second one is to provide a modern microprocessor with some faults in it. And my job for this summer is to inject faults into a modern microprocessor and be able to enable them at runtime. Here are the hardwares I'm using. This is an Xilinx Vertex 5 board. It has a serial port that can be connected to a normal computer, and we can use tools like a hyperterminal to read the output from it and serve as the screen. And in the middle, there's a silver component, which is an FPGA, field programmable gate arrays. The difference between an FPGA and a microprocessor is that a microprocessor is designed and optimized to perform certain functions, and its functionalities are fixed, while an FPGA is reprogrammable, so we can change the functions at any time. And this feature works perfectly well with our second component, which is OpenSpark, a modern 8-core microprocessor designed by Sun Microsystems. It is open source so that we can modify it as we want. In our case, the modification will be fault injection. With these two components, we've got a simple computer. Don't underestimate this thing. It can run Ubuntu and OpenSolaris, but it's just very slow. So I guess the next question is, how do we inject faults into the FPGA? I'm not going to go deep into details, but the basic idea is to use a logic component called multiplexer, or in short, MUX. We connect the original signal from the microprocessor to the top wire on the left. And this original signal is randomly picked inside the microprocessor. And then we connect some faulty signal to the bottom wire on the left. On the right, it is output signal. And by controlling the control signal and setting it to some values, we can either connect the original signal to the output, or we can connect the faulty signal to the output. In this way, we have controls over several important matters. We know where the faults are injected. We know how to control these faults and which one of them is enabled at runtime. And more importantly, we know whether the software detection is correct. Up to this point, my job is almost done, and the next step is to cooperate with University of Illinois and run some software tests. At last, I have a few thoughts to share with about my summer research experience and how it is different from our normal courses. In class, I feel like everything is set up well by someone. We don't have to worry about the software that we are using or the compilers we are using. We can always focus more on the coursework. And more importantly, there's always someone who knows the solutions. While in research, there's definitely more frustration. A lot of unexpected things could happen. It is possible that nobody could help. For instance, we still have a post on Science Forum that nobody has replied yet. However, the fun of research is that it is original work and it is practical. We could always work on a project that we have interest in. So I guess in the future, I will still go to grad school and keep on doing some research.